Hello friends, here with your two-handed wave. It's Darcy. We are going to talk about phases and enthalpy today. So we're going to use a TS diagram. So T, this is just simply what you'd think of, temperature. And this down here for S is entropy. And before we dive into what is here, what we're looking at, I want to talk about entropy because it is a difficult property to visualize. It's something I still struggle with. So we're going to start with a simple definition. We're going to work together throughout this course to really solidify what entropy is and what it can really tell us about the phases of, in this case, we're going to look at the phases of water. But so entropy is just simply a thermodynamic property that increases whenever heat is transferred in or into, I guess it would be in, whenever transferred in, or friction is present. And the only way it decreases, so it decreases only when heat is transferred out. So a thermodynamic property that increases when we put heat in or that there's friction, and it decreases only when heat is transferred out, which makes sense because we can't reverse friction. Friction's only like an input. It's only when we take heat out that it decreases. Okay, so jumping back to this diagram, so we have temperature, we have entropy. We have this line going through this is called our vapor dome. We're going to assume this is for water. This is going to walk us through the phases of water. So this is our vapor dome, and then we have this line of constant pressure. So in this case, let's just say it is 14.7 psi. So we're just at atmospheric pressure. And we can look through, we can think of a situation where we're just picture this. This is how we're going through the phases. We just have a pan. This is a hot surface. We have a pan of water, and we're going to go through the phases of this water. So let's say we know that the boiling point of water is 212 degrees Fahrenheit. But let's say that we are at maybe 70 degrees. So if we come across here and draw this dot here, we are going to be in a phase called subcooled liquid. So I'm just going to put SCL. That's a subcooled liquid. So in this, it is 100% liquid. It is just water. But as we progress up this line of constant pressure, we're going to get to this point where we start to intersect this vapor dome. So this is when the water starts to boil. So if we dot over here to our temperature, we're going to now be at 212 degrees Fahrenheit because we know at atmospheric pressure, that's when water boils. So at 212 degrees Fahrenheit, we are going to call this the saturation point or the saturated liquid point. So this is going to be saturated liquid. So it's at that point, it's boiling. We're still just at that baseline of when vapor starts to form. We're still at that liquid phase. But as we travel across this from the point of saturated liquid point over to this other point over here, which we'll talk about, we're going to call this a wet vapor. Wet vapor. And if you notice, the temperature isn't increasing in this part of the vapor dome because we're just getting more and more vapor. So the energy from this heat is going into breaking bonds instead of raising the temperature. So that energy that is going in is now breaking bonds. And say like right here, we'll be at 50% liquid, 50% vapor. So that tells us where we are across that line is depending on how much of a vapor, what portion is a vapor versus what portion is a liquid. So once we get to this point, this is now just the opposite of saturated liquid. It's going to be a saturated vapor. So this is when 100% of our liquid has turned to vapor. It's 100%. After this point, that energy that we are putting into the system can now cause the temperature to raise. We're still at that same pressure, but we're going to end up here somewhere. And what we call this up here is going to be, we're going to put SHV, because it is a superheated vapor. So in this stage, we are above the temperature of boiling. We have now boiled off all of our liquid. We're now just increasing the temperature of that vapor. So we can look at this in context of the energy equation, first law of thermodynamics. So if we look at that, I'm actually going to do a quick erase here of entropy so that we can use more of this board and it's not in our way. Rewind if you need the definition. So, guess I should just go all the way. So we're going to look at the energy equation. So if you think back about what that is with context to thermo, we are going to have some potential energy to start out with. We're going to have some kinetic energy to start out with. We are going to have some internal energy. And I guess I could do this at stage. Let's do this at 1. So we're at the first point. And then you're going to have some work in. You're going to have some work out. Or on and by. Sorry, I'm always confusing those two things. So then we have some Q in. We can put rates on these. We have some Q out. We don't have to have either way. We're not going to talk about units right now, so don't worry about that. But, okay, so we have all of those things, and then we will end up with a potential energy 2 plus kinetic energy 2 plus internal energy 2. I didn't do these. This is confusing because I didn't do them in all the same case. Let's put these in lowercase as well so that we're talking about that same specific work. Okay, or specific energy. Okay, so when we look at this overall equation and thinking about state 1 versus state 2, we can think about this is our stored energy beforehand, and this is our stored energy afterwards. This is our transient. So let's put transient, stored, and stored. And in thermodynamics, the nice thing is potential energy and kinetic energy are usually really small, really negligible. So we can just get rid of potential energy and kinetic energy. So that's going to be our first takeaway. So we get rid of those potential energy and kinetic energies. So we are then left with U1 plus work on minus work by plus Q in minus Q out equals U2. So with work, there's two types of work. So there is shaft work. So we can think of this as something like if we think about the Rankine cycle, we have steam coming into a turbine, it's spinning around a shaft, and we're getting some sort of work out. Or in a pump, we have to put work in to be able to pressurize that water or whatever if we think in the cycle. So that's shaft work. But there's also, if you remember back to fluids, something called flow work. And what flow work tells us is that we have some sort of, like if you had a pipe and we have a high pressure on this side and a low pressure on this side, we are going to have some sort of pressure difference causing a force over that distance between that high and low pressure. So that's going to be flow work. And if we look at the equation for flow work, it's going to be simply equal to pressure times volume, specific volume. I'm going to clarify that because, again, that is a weird little V-looking letter. Specific volume. So when we look at our equation here, we want to make sure that we include both of these. So we are going to have U1 plus work on plus P1 V1 minus work by plus Q in. My marker needs a little more ink, minus Q out. And I already subtracted work by, so then we have, and I guess we can do, this is where you can decide whether you like the subtract or put it on the other side. So this would be P2 V2 is equal to, I'm full of sneezes today, oh man, is equal to U2. So if we look at our shaft work, this is going to be our shaft work, or this one. Whereas this, our PV values, are going to be our flow work. I should have done that in a different color, but you get it. So here's flow, here's shaft. So when we look at this, we can actually do a grouping, and this is where enthalpy comes in. So enthalpy is simply equal to U plus PV. Convenient that we take two of these terms, group them into one. So, and I guess that can, I'll give you the definition here. So enthalpy is simply a convenient grouping of internal energy and flow work. Wow, what a definition. It's just a convenient grouping of internal energy and flow work. So if we put that back into this equation up above, we are going to end with an equation coming straight from the first law of thermodynamics of H1 plus work on minus work by plus Q in minus Q out is equal to H2. So there is your equation. I'm losing steam here in my pen. There is your equation for the first law of thermo. There's our simplification for thermodynamics. Lots of times this is all that there's going to be because of those negligible potential and kinetic energies. We're just going to consider the enthalpy, the work on, the work by, the heat transfer. That's it. So, as Ron likes to say, it's all about that H. So remember that for enthalpy. It's a very useful property that we'll talk about more in the upcoming videos, but that H can tell us about where we are on our line of constant pressure within our vapor dome.